In this video, we're going to talk a little bit about the features of the adjacency matrix. So consider the following network of friends, Bob, Callie, Denise, and Ed, for which we have the following adjacency matrix. So row 1 represents Bob, then Callie, then Denise, and then Ed. And column 1 represents Bob, and then Callie, and then Denise, and then Ed. And a 0 in a specific entry tells us that those two people are not friends, and a 1 will tell us that they are friends. For example, we see that Bob and Callie are both friends, and Bob and Denise are both friends. And if we construct this into a graph, putting an edge between two vertices, if and only if we see a 1 in that position, we get something like this. So for example, Ed, we see that Ed's row, which is the 4th row here, Ed is only friends with not Bob, not Denise, not Ed, but is only friends with Callie. And so what we notice is that Ed is sort of an outsider in the group, that he's only linked to the group via Callie. Now, from an advertiser's perspective, that might not be so bad because Ed is still connected to the network. All right, so then let's think about what happens whenever we square or cube this matrix. Now, we should point out that the square of a matrix is not simply the square of each element. We're not going to discuss the process of matrix multiplication here because you can actually take a matrix A and you can square it or cube it in any graphing calculator or computer system, and it will do its due diligence. So we can see obviously that A squared is not simply the square of the elements because we just end up with a bunch of zeros and ones. So we start to investigate this and we want to think about what do some of these values mean intuitively. Well, if we look at the diagonals and we see that the diagonals from top left to bottom right seem to tell us something or some piece of information. And in this case, if we go back to the adjacency matrix, we see that we can relate this and see that Bob to Bob here has a value of 2, Bob to Callie has a value of 3, or Callie to Callie, Denise to Denise, and Ed to Ed. Now, what this actually happens to tell us is the number of edges that extend out of that particular vertex. So we see that for Bob, we see that Bob has 2 edges, in other words, has 2 friends. Denise has 3 friends, Callie has 3 friends. We see that's 3 edges emerging from Callie's vertex. And a similar process for Denise. Denise has 2 friends. Ed only has 1 friend. What we really care about, these values are really only trivially important and only in the A squared matrix, and even then it's arguable exactly what they represent, but they do tell us the number of edges extending from those vertices, so that's a useful piece of information. But what we actually can tell from this is, in general, A to the n tells us the number of paths from person I to person j, where we're not talking about a person to him or herself, of length n. Okay, so for instance, we see that this value of, let's pick on this one right here. This one tells me that there should be exactly 1 path of length 2 to get from Bob to Ed. Okay, we know Bob and Ed aren't friends, but if we look how we could get to Ed, we can see that if Bob is connected to Callie and Callie is connected to Ed, that's a path of length 2 to get from Bob to Ed. So there exists only 1 path of length 2 to get from Bob to Ed. I can't go Bob to Denise and Denise to Callie and Callie to Ed because that's a path of length 3 that requires a traversal of 3 edges. So similarly, we see that, for example, in this case, this would represent Callie to Bob. Okay, so from Callie to Bob, I should be able to find 1 path of length 2 to get from Callie to Bob. Well, I see I can do it in a path of length 1, but I also see that I can, Callie and Bob are also connected through Denise, so there is exactly 1 path of length 2 to get from Callie to Bob. A cubed, similar process. So here, for example, this 4 represents, this is from Callie to Bob. This tells me that there are 4 paths, there are 4 different paths to get from Callie to Bob in a path of length 3. Okay, so let's see if we can count those. So Callie to Bob, you can get there by going Callie to Bob to Denise back to Bob. Callie to Bob, Denise back to Bob. So that requires 3 edges, right? That's kind of trivial because it I can connect Callie and Bob in a shorter path length, but if I go Callie to Bob to Denise to Bob, that's a path of length 3. Similarly, I can go Callie, Denise, Bob. Oh, I can't do that. Let's see. So I could go Callie, Bob, Callie, Bob, Callie, Bob, Callie, Bob. That's also a trivial path, but it is one of length 3. And I can go Callie, Denise, let's see, Callie, Ed, Callie, Bob. That's a path of length 3. And there's going to be one more as well. Let's see, I can go, can I do Callie to Denise, Callie to Bob, Callie, Denise, Callie, Bob. So there are my 4 paths of length 3 to connect Callie and Bob as the last vertex. So really, this is not useful in terms of friendships per se, but it does tell us that I can get from Callie to Bob in a path of length 3. It doesn't say that we can't have redundant edges, it just says that there are 4 such paths. Okay, so that's useful because now we can see really quickly how fast we can connect 2 people in the network. So what is the really significant thing a cubed tells us? Well, if we look at a cubed, then we see that every person in the network can be connected to every other person in the network via a path of length 3. Now remember that we said that the diagonals were useful in a squared. They're not going to be useful in a cubed. So forget about the diagonals in general. Those are not useful. I mean, we could still say that you can get from Bob back to Bob in 2 different paths of length 3, but we don't really want to get from Bob back to Bob. So we often ignore those diagonals. So we see that if we consider all the off diagonals, that every person can be connected to every other person in the network via paths of length 3, at least one path of length 3. So this is what we call 3 degrees of separation. There exists 3 degrees of separation between any 2 people in the network. So that's pretty good, right? Because even though Ed is sort of an outsider, Ed is connected in the network by a friend of a friend of a friend. So think about that a friend of a friend of a friend connects everybody in the network. So if you advertise to one person, ideally, inevitably, that message would get to everybody else in the network as well. Well, we can also add matrices together, a plus a squared. So if we did that, let's see what we come up with. Now, addition of matrices is really intuitive. It's just adding the corresponding entries in A with the corresponding entries of A squared. And what we get when we do that is we get all these non-zero entries. So what exactly does this mean? Since A means the number of, A tells us who's friends with whom, and A squared tells us who can be reached from what other person by a path of length 2, we see that everybody in the network is connected within a path of length 1 or 2. So with a path of length 1 or 2, a direct friend or a friend of a friend, everyone in the friendship network is associated. That's good news. We can tell that everybody, if they're not friends, they're definitely friends of friends, and that would tell us that the minimum, what we call the degrees of separation, how many friends of friends people are connected by. We know that we would say that this graph or this system has excuse me. Let me try to rephrase this. We know that everybody in the network is separated by no more than 2 degrees of separation. So we would say that this friend network has 2 degrees of separation by the fact that within a squared, everybody in the network is connected to everybody else. So that's pretty valuable information. It tells us a lot about a network, and this could be, again, any network, and it tells us that every vertex is accessible from every other vertex by a path of length 1 or a path of length 2. So you got to think about these as we don't know by looking at these whether 2 people are directly connected unless we go back to the original A matrix, but we do know that this 3, for example, represents the fact that Bob and Callie are either direct friends or they're friends of friends. And this tells us the number of paths of such paths that exist. Okay, cool. So let's take a look at the concept of a directed graph. So a directed graph is, let's think about why this would be useful. So often vertices can be connected, but the flow of information is not in both directions. So think maybe of like a computer system. Not every single piece of a computer communicates with every other piece. You can think of one-way streets where travel can take place in one direction but not the other. Phone calls from telemarketers, control systems, tasks in a project. You can't do the later task first and then work your way backwards. So we have a couple of pieces of information that we need, some vocabulary. We say that the in degree of a vertex is the number of directed edges pointing towards a vertex, and the out degree is the number of directed edges pointing away from a vertex. So now we have to take into account direction, and it's not as simple as just saying the degree of a vertex anymore, but we have to be specific and say in degree or out degree. A directed graph is strongly connected if there exists a path from every vertex to every other vertex. Doesn't matter how far a vertex is away from another vertex, it just means that we could ultimately get there by using directed edges. So here's a microcomputer system. We have a CPU, we have memory, we have input and output, and we see that the CPU sends information to the memory, and the memory sends information to the CPU, but anything that's inputted or input into the system will, in this case, send that information directly to the memory, but the memory doesn't communicate back with the input. There's no need for that. Similarly, memory sends stuff to the output, but the CPU doesn't send stuff to the output, and the output doesn't send stuff back to the memory. So this is how this particular system works. Our question is, how could we represent this graph with an adjacency matrix? Well, much in the same way, except we're only going to put a 1 in an entry if the component, here represented by the row, has an edge that terminates at the particular component of the column. So for example, we see that the CPU communicates with the memory, so CPU and memory, we'll put a 1 there. But for example, input communicates with memory, so input has a 1 here in its particular row, but because the CPU or the memory doesn't send stuff back to the input, we see that for row memory and column input right here, we see that the memory does not send any information to the input. The memory only sends information to the output and to the computer. Same thing for the output. The output doesn't send information anywhere, but the memory does send information to the output. So the difference is that we don't just have, it's not going to be a symmetric graph necessarily, because not all communications are bidirectional. So now we could start to talk about, well, what is a squared for the microcomputer system and what does it mean? And will there ever be a sum of matrices such that all values are non-zero? Why or why not? Well, let's take a look at a squared first of all. I'm going to use GeoGebra here, or excuse me, Octave Online. I'm going to create this matrix by typing in the values in that matrix. So we create a matrix this way, 0, 1, 0, 0, semicolon to start the next row, 1, 0, 0, 1, the second row, and then the third row, 0, 1, 0, 0, and 0, 0, 0, 0. Okay, so I've just created that adjacency matrix. If I take a look at a squared, this tells me how many paths there are from one component in the network to any other component in the network. So for example, we saw here that the CPU was sending information to the memory, but we see here that the CPU does not send information to the memory. There's no way to get information from the CPU to the memory in a path of length 2. And we see that in the image, that I can send information from the CPU to the memory, but there's no way for me to get message from the CPU to the memory by going through some other component first. Also, we see that here that this 1 here now represents the memory sending information to the memory. Well, that's interesting. So that means there's one path of length 2 to get information from the memory back to the memory. So the way that can happen is if information goes to the CPU, that's a path of length 1, but then from the CPU back to the memory, that's a path of length 2. So I see that the memory can communicate back to the memory via the CPU. Now, the final question here that we have is, will there ever be a sum of matrices that all values are non-zero? Well, no, there won't be, because you can't get information from the input back to the input, no matter how hard you try, no matter how many paths there are. I can keep send information to the memory, but then it could just circulate between the CPU and the memory, but it can't ever go back to the input. So as we said, that we cannot connect every piece or every vertex to any other vertex in the graph, because once again, for example, the CPU and the input, no matter how many times we multiply A by itself, it's going to be impossible to get information from the CPU to the input. And we wouldn't expect that. We wouldn't want that. Similarly, it's impossible to get information from the output to any other vertex in the graph, because information does not flow from the output to any vertex in the graph. So how about if we start talking about Euler circuits? Do Euler circuits exist? So let's think about the graph below. So if I wanted an Euler circuit, we know that we need to be able to get from any edge or any vertex back to itself by traversing every edge exactly once. Well, in this graph, I can see that, all right, if I start at A, then I can go A to B. I can go from either B back to A. Well, that's my only option, right? So I go B back to A. And then I can go from, let's say, A to C or A to D. So let me go A to D here. Excuse me, A to C here. So I'll go A to C. And then from C, I have basically two options. I can go from C to D or C to B. However, the thing that I notice about vertex B is if I arrive back at B via this path, and regardless of how I arrive at B, I notice that once I've arrived at B for a second time, I can no longer leave it without walking the same edge that I've already walked. So we notice that B has an in degree of 3. So I'll just say I degree, or IDG, is equal to 3, but the out degree is equal to 1. So that means I can, sorry, I have that backwards. No, I don't. The out degree is 1. So I notice that I can arrive at B once, right? So I can basically take care of one of those in degree edges. And so I have 2 in degree edges left that I can walk on, but then I have to leave vertex B, and that leaves me with 0 more out degrees. So once I've left B, I can still arrive at it twice, but I can no longer leave it without going over the same edge again. And so I notice that that's not possible in this case, regardless of how hard I try, to be able to take care of these 4 edges that connect to B. I would have to repeat one of the edges that has for the out degree. So this poses an important question. Although B had, if you think about it, the degree of B is technically 4 because it has 4 edges that connect to it. Because we have to start to look at as directed graphs in terms of in degree and out degree, I'm not going to be able to do that even though B has an even degree. So what would be necessary? Well, in this case, it's kind of cool because as long as the in degree, the number of edges leading into B, is the same as the number of edges leading out from B, then I can arrive and leave an equal number of times. So that's our little theorem here. An Euler circuit will exist as long as the in degree of each vertex is the same as the out degree of each vertex. Well, this actually implies that the vertex will have an even overall degree, because if you have, say, an in degree of 3 and an out degree of 3, that means you technically have 6 edges, but the direction of those edges is very important. Except it is not enough to only have even degree, since an in degree of 3 and an out degree of 1, for example, like our vertex B, means you can arrive 3 times, but you can only leave, leave once. So with that said, Euler circuits can be found for directed graphs, but how about Hamiltonian circuits? Well, we didn't talk much about Hamiltonian circuits with respect to graphs, so it becomes a little bit more complicated to talk about them for directed graphs. And not only that, but we already know that the existence of Hamiltonian circuits, there's one theorem that tells us that the average degree of a vertex needs to be at least the number of vertices present, and that gets a little bit more complicated. So we won't really talk about Hamiltonian circuits. That's still a fairly open problem in graph theory. So we'll go ahead and stop there. Hopefully this has been helpful and has gotten us acquainted with the idea of adjacency matrices for graphs and for directed graphs.